All right, today we're going to talk about counting fish in a slightly different way. We are going to be counting fish using mark and recapture. And the idea is that there's some unknown population of fish out there. We're going to catch some of them. We're going to tag them or put marks on them somehow, re-release them into the environment, and at some later date, again, catch some, look at the number of marks that we have, and make an estimate of what the total population is. So we're going to first give you a method that is called the Lincoln-Peterson estimator. This is probably the simplest estimator. And what we need to do is first just establish our n, which is going to equal 1,000. So this is our true number of individuals in a population. I'm just picking 1,000. So this is the number of fish in the population that we're interested in. Little n is going to be 50. This is going to be the number of fish marked on our first visit. Big K is going to also equal 50. And this is going to be the number of fish caught or sampled on our second visit. And then little k, I'm just going to put this as a hashtag because we're going to get to that a little bit. We're going to compute this, is the number of recaptured animals that were marked. So it's the number of animals that came from the sample K that were actually remarked. Now there's some important assumptions here to this estimator. One is that the samples are random. We also assume no death, no births, no migration. Okay, so this is like fish in a pond, so to speak, that are growing slowly. So how do we go ahead and do this? Well, let's go ahead and make our population. Let's just call it pop. And what I'm going to do is I'm going to repeat 0, and the times I'm going to repeat it is n. And this is going to represent, so zeros are our unmarked fish, and ones will be our marked fish. So right now, we have just run all of this. We have a population. This is our unmarked fish. There's 1,000 zeros. So these are 1,000 fish. None of them have a mark on them. And let's go ahead and mark fish on our first visit. So let's take our population, index 1 to little n, so that's 50 fish, and we're going to say that equals 1. So if we run this and we look at our population again, you'll notice that the first 50 fish that we pulled out here, we are marking with 1. An important element of the next step here is that we're going to take our population and we are going to permute it or mix it up. We're going to use the function sample to do that. We're going to sample pop, and we're going to sample it n times. So we're going to take 1,000 samples. That's going to be without replacement. So if we can just do a quick question mark sample. It takes a sample of a specified size of elements. We're going to take this, x is our population, and the size is the number of items to choose. All right, so when we do this, you'll see that our population now has the ones randomly mixed into it. And that's supposed to simulate, say, okay, the fish that we put back in aren't just all hanging near shore again, where they're going to be caught easily again, but they have dispersed into the population. Okay, so when we come back on our second visit, we are going to go ahead and compute something called our sample, which is, again, we're going to sample the population, and we want to catch a number of fish on our second visit, so that's going to be K. We're going to pull 50 of those out. Let's go ahead and hit run. And when we look at SAMP, we're going to get 50 of those things, some of which have marks on them, some that have marks. All right, we need to now estimate our little k, which we're defining just the number of recaptured animals. All we have to do is take the sum of SAMP. That's going to add up all of the zeros and ones. And of course, ones are our marks, so K is 5. We sampled 50. 5 of them are marked. So our population estimator looks something like this. We take K, that's how many we caught. We multiply that by N, which is the number of animals marked on our first visit, and we're going to divide that by little k. When we do that, our population estimate is 500. So based on this analysis, we have estimated a population size of 500, but we know that our real estimate is 100. So we did not a very good job. But again, that's based on the random sampling that we do, both as the fish mix in the population and as we sample. So if you just run this again, in fact, I'll just put here, run it again, you'll get a slightly different answer, 833, and run it again, and you'll get 500, and run it again at 625, and 833, and 2500. And you'll see for this number of fish and the number of fish caught on our first visit, it is not that reliable of an estimator. So there's a couple things we can do to change that. We can increase the number of marks. So maybe let's put 100 marks out instead of 50. And maybe we can capture now 100 fish on our second visit. That would be about 10% of the population. And you can see, all right, look, we got a much better estimate. There's 625, 1400, 1400 again, 1100, 1000, 714. So there is some error. Now, there are ways to compute confidence intervals in this. I'm not going to do that because I'm going to take us to the next method, which is called the Schnabel method. What is the Schnabel method? Well, the Schnabel method recognizes that just a single tagging event and then a single resighting doesn't give you maybe the best estimate. So the Schnabel method is designed to do multiple tagging and revisits to generate an estimate. The way to think about this is that we're going to capture fish. We're going to take basically a Peterson estimate, put more marks out, take another Peterson estimate, put more marks out, take another Peterson estimate, and you basically do an average of those things, and you'll see that work out in the math. So let's start again. I'll just do remove list equals ls. So n is going to equal 1000 again. This is going to be the number of fish in the population. All right, large K, I'm going to make it 20, and this is going to be the number of fish captured in each visit. And V now is going to equal 10, which is going to be the number of number of visits that we make to make an observation and to put new tags out. So, like previously, we're going to generate a population that is unmarked. We're going to repeat 0 times equals n. And we have to define some parameters that we're going to keep track of. One is called C sub t. That is going to be a null vector. You'll see that we append to this. This is going to be the total number of individuals caught in sample at time t. That's how many we're catching out of the pond or out of the ocean, time t. In this case, it's going to be 20 every time. We're also going to do one called RT. This is the total. It's going to be null. This is going to be the total number of individuals already marked in caught sample t. Okay, and UT. So RT is going to be, hey, we caught a sample. How many of those are already marked? UT is going to be, again, let's make that null, the number of individuals marked for the first time and released at sample t. So the idea is that first of all, we go to our pond, nothing's tagged, we catch 20 fish, we put 20 tags out. We go our second time, we catch 20 fish, 2 of them have tags. We record that, we put 18 on the remaining 20 fish, put them back out, come back a third time, maybe we catch another 20 fish, 4 of them have tags, we put another 16 on those, so that's what this is, the number of individual, I should probably spell that right, individuals, oh, not married, marked, maybe that's the same thing for the first time, okay, all right. So we're going to create a loop here for time in 1 to v, which is going to be the number of visits that we have. We're going to keep track of a couple things. The first thing we're going to do is say that CT, let me take some space out of here. CT is going to be the concatenation of what was in CT previously, which is null, with our K, that's the number of fish captured in each visit. Our marks is going to equal that we sampled is going to be the sum. Sorry, let me do this. Yeah, we want to sample the population, K times, and we want a sum of all the marks that exist. Now at first, when v equals 1, there's going to be none in there, right? So, or I'm sorry, when t equals 1. So t equals 1, CT is just going to, oh, I guess I got to create these. Create all of these. CT is just going to append to K, which is 20, and how many marks are in the population when we sample it? Well, there are 0 marks. Nobody has come and marked this before. We need to now keep track of RT. Remember, RT is the number of individuals already marked in sample T. So that's RT is going to equal C RT and marks. So the first element's going to be 0. our new marks that we put out is going to equal K, the number that we sampled, minus marks. So this is, we pulled 20 fish out. How many marks did we get on our first sample? 0. So the new marks we put out in our first time step are going to be 20. UT, we're going to keep track of new marks we put out. Right. Now, what we have to do now is create an index. We want to find an index of which animals are marked in our population. So I'm going to do which population is not equal to 1, right? Which of those are not equal to 1? Let's just run this. Well, they're all not equal to 1, so it's going to ask what index is it, so every single one. We're going to take the first one. How many new marks do we need to put out? We need to put out 20 new marks. We're just going to take the first 20 of those. That's going to be our index. Oops, new marks is not found. So our index for those are the first fish that we're going to mark, just 1 through 20. That's the index. So pop of our index is going to equal 1. We'll do that, and we'll see that we have tagged the first 20 fish in our population, and then we're going to permute it. Population, sample, pop, and I want to do it n times the number of fish in each population, in the population. So we're just mixing them up. There they are. Okay. That's what we need to keep track of. So let's walk this through here just a little bit. NT. All right, so let's start up here again. Just clear these out, rerun them again. So when t equals 1, you'll see that, I'll run this one, you'll see that CT now has 20 in it. The number of marks that are going to go in. There are no marks that are out in there, so RT, the first element, is going to be 0. New marks that we're going to put out is 20. And we're going to keep track of our new marks with UT. First element's 20. Now we're going to ask which population is not marked, is not a 1. All of them are like that. Oops. All right. And our population, we're going to mark our population and mix it up. Now we have that. Okay, so now let's go to t equals 2. And we'll just work back up here. CT now that CT has 2 elements in it, right? Because we appended whatever was in CT before with another K, now that t equals 2. The marks, how many marks did we sample here? We got 1 mark, okay? So these were the marks that were in the population from our 20 samples. So we sampled 20 fish, we got 1. So the new marks that we put out, we're going to put 19 new ones out. We're going to keep track of the new marks that we put out. Oops. Don't want to run that twice. So we put out 20 the first time, 19 the second time, because in our sample the second time we caught a fish that had a mark. And then we're saying, okay, which of these All right, we need 19 ones that have not been marked yet. All right, so there we go. Just need the first 19. We're gonna mark them and mix them up again. Pop. Okay, so now we've got a few more in there. So if we look at the sum of pop, you'll see that we have 39, which is we put out 20 the first time and 19 the second time. We're going to do this 10 visits. So I'm just going to come back up to the top and run this. All right, and we'll see that CT is 20 every time. That's how many fish we're pulling out. RT, that's the number of individuals already marked in sample T. So the first 3 times in this case, we didn't get any. Then we got 3, 1, 3, 3, 4, 6. So it's slightly going up. And new marks that are going out are 20, 20, 17, 19, 18, 17, 17, 16, 14. Okay, what else do we need? What else do we need? Well, we need to know another element called MT. And what is MT before we define it? So this is the cumulative number of marked individuals in the population before sample T. A cumulative number of individuals. So there's a great way to calculate the cumulative number of individuals. We're going to use a function called sum, a cumulative sum. Cumulative sum of, I don't know, marked individuals in the population. Well, what's UT? The number of individuals marked for the first time and released. So if we look at UT, this, at time 1, that's how many we marked, and then we did another more, so then we had 40, then we had 60, right? And then we had how many? 77, and so on. So we're going to do the cumulative sum of UT. Let's run this right here. Okay, right, so here's the cumulative sum. So 20 was the first one. Look at the second element, it's 20 plus 20. Third element is 20 plus 20 plus 20. Fourth element is 17 plus 20 plus 20 plus 20, which is 77. Fourth element is 19 plus 17, so on and so forth. That's the cumulative sum. Now, what's tricky here is this is the cumulative number of marked individuals in the population before sample T. Before sample T. So what's the at time 1? What's the cumulative sum before we sample? It's actually 0. So I have to append this here. Let's do this. Let's do C. Let's put a 0 on the front of this vector before we sample, and you'll see that now we have a 0 there. And so now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 points. We know we're only visiting 10 points, but there's the way to think about it. What, on time 10, what was the number of tags that were already out there? It was 164, and then we put 14 more out, which got us to a total of 178. So we don't need this last element, 178, because we want to know the cumulative number of marked individuals in the population before sample T. Before sample T. So I'm just going to put an index here, and I'm going to say, give me the first 1 to V elements, 10 elements. So if I do this now, you'll see that it just gives, with the 0 in front, it gives me up to 164. We're going to go ahead and make this equal MT. MT. We'll make that an object. All right, so the calculation is quite similar to what we had before. You'll see we're going to take our CT, which is the total number of individuals, times our NT, which is the number of marked individuals in the population. This is really similar to the Peterson estimate, right? So N is the number of fish marked, so that was this formulation, K times N, so that's the number sampled, the number marked, But now we're going to multiply these together. Remember, these are vectors now, right? So I have a series of 10 elements here. And so I'm going to multiply these together, and I'm going to take the sum of them, the sum of these guys, and we're going to divide that by the sum of what was in the Peterson. It was K. What was K again? The number of recaptured animals that were marked, right? And what do we want to know? We want to know, in this case, RT, the total number of individuals already marked. Really poor spelling here. And marked in caught sample T. So I want to know the sum of RT. But that should do it. That should do it. And so if we do that, that gives us 772. There's a slightly different calculation here, which is the sum of CT times MT squared divided by the sum of MT times RT. And this is a slightly different formulation, slightly different estimator. In this case, it gives you something really simple, really similar. And I'll tell you about that in just a second. But for now, we can get these two estimates. We just run this again. Remember, the n is 1,000, so we're getting 1,742, 1,500, 1,100, 800, pretty close to 1,000. And there's another, what I want you to do now is there's actually a program that will do this for you and compute confidence intervals. I'm not going to take you through that in this video. If you go to Tools, Install Packages, and click and go ahead and do Fish Methods. So go ahead and install and make sure you have the dependencies. So go ahead and do that. And then go ahead and require Fish Methods. And here's the function. It's called Schnabel. S-C-H-N-A-B-E-L. Schnabel. Our catch, what do we catch? That's going to be CT. Our recaps, it's going to be RT. Our new marks is going to be UT. And alpha equals 0.05. So that means we're going to calculate this 95% confidence interval. Let's go ahead and require Fish Methods. You'll see that there's a bunch of packages that it requires, and then run Schnabel, and you'll see, yeah, look, here's the Schnabel method, here's the Schumacher-Eschmeyer method, which treats this a little more like a regression. You can read about that on your own. But they give you lower confidence intervals and upper confidence intervals. So we know that the right answer is 1,000. The lower confidence interval is 916. The upper is 2,900. So, maybe not so great. But you can come over here and you can adjust this. So let's suppose that we visited, you really like field efforts, and you want to go out 20 times. Come over here, and you'll notice that, yeah, your estimate's a little bit better. And in fact, you can kind of check that too, right? So if we can just plot over your visits, 2 visits of your CT. This is how many you're catching each time, right? We know it's constant. And we can plot, well, just copy and paste this. CT, RT. So what's RT again? RT is total number of individuals already marked and caught in sample T. This is going to be UT, which is the number of new marks that we're putting out. And MT is our cumulative marks. So our RT here, you can see that As our visits go and we keep sampling, we're getting more and more fish back in our, more and more recaptures back. And this is the number of new marks that we're putting out. At first it's 20 and then it starts to decline. And this is the cumulative number of tags that are actually going out, right? So we've got something over 300 tags that we're putting out there. And so with 300 tags on 20 visits, are you happy with these confidence intervals? Well, that's an interesting question, right? So how well do you need to know the population? So let's suppose you have not 1,000 fish in the population, but maybe it's on the order of 1,000,000 fish in a population, and you've got 20 visits. This is probably more like what it's actually like to do this kind of work. And you'll see that that's not enough. We're getting infinite. We're not good estimators. We haven't recaptured anything. So we didn't put out any. We didn't need any recaptures. You can try it again. Still, no recaptures. It's just not enough. So we got to put out more tags if you've got 1,000,000 fish. So let's put out maybe 200 or 200 fish captured each visit. Maybe that's a little more reasonable. You use a big net. Okay, so what's your estimate here? Your estimate is 1.2 million. This one is about 1,000,000. Their lower confidence is 690,000. Upper confidence is 3.7 million. So yeah, the real number is 1,000,000, and you guys can play around with these numbers to see, what do you need to actually get good estimates of fish populations. Again, this has the same assumptions that we had up here before. Samples are random, there's no death, no birth, no migration. And so even with those very strict methods, you really got to sample pretty hard. You got to put out, you got to catch 2,000 fish per visit. And you're going to do that 20 times? That is a serious field effort. And now we're getting a little closer. Right? So it gives you a sense of the scale that you need for these different methods. So I'll just put this back at 1,000. I'll leave it at that.